Good. So we start from what we left from previous session. I won't continue with assigning or the wind load because it's not as important as other types of loading. Okay. I will assign non-deformed shape, and I want to have this and the releases. Okay, and also here. Now, regarding the masses, you need to go to define mass source, and for the modal analysis or modal response spectrum analysis, okay, for seismic action and design, we need to assign the masses. Here it's the mass source. We go to modify, and we need to specify from which loading patterns we take it. Okay, here are two distinct options: element self mass and additional mass, or specified load patterns. Depending on how you worked with loading patterns, okay, you go with checking also the first one or only the last. I will go with only the last because I input it in dead all the permanent loads. Okay, and if I put also this, it will take twice the self weight of the element. That's why, okay, because I have dead with self weight multiplier of 1. So I need not to put that, only this. The combination for the masses, it's basically the seismic design combinations without taking into effect the seismic load. So we have partial safety factor for the permanent as 1, for the live 0.3, and if we have snow or not, function of the roof, how it's considered, okay, if it's open terrace or not, we go with 0.4 snow or not. In our case, I am considering only live as open terrace, so I have 1 and 0.3 for the live load, okay, and this is my mass. Now for the other method, what I mentioned, for example, if I want to add here at one joint, okay, in the corner, lumped mass, I need to select the joint, assign joint masses, okay, and here I will assign as mass, and I will specify the translation on the two directions. Why? Because mass, it's correlated with inertia, okay. You can neglect the vertical component even in seismic action in most structures, with exception of bridges or long elements, or if you have, let's say, towers that have spans, okay, they have arms, okay, with the coats arms, okay, and that might have vertical effect. We are not in the case, so we should specify only that. Take care of the units, okay, because you have here tons. If we go with forces in kilonewtons, acceleration, gravitational acceleration in meters over square seconds, we get the unit in tons. This is as let's say what you're used to with consistent units from seismic design, okay. So just take care if you want to specify like that. Now, further on, regarding definition, we have, let's say, seismic loading, because we haven't discussed how to assign seismic loading. I understood from Professor Dino that you discussed a bit regarding that. I will show you how to input it using your values into options, okay. So you go to functions, response spectrum, okay, and you need to define your spectrum. You either take something from here, okay, or you can define a user spectrum. It's just a function. If you have, for example, two structural systems with two different factors, like moment resisting frames, okay, with 6.5, let's say, in ductility class high, and X frames with Q equal with 4, okay, you need to specify two functions. Let's say Timișoara moment resisting frame, or moment resisting frame without, to have it shorter, okay, without the name, and you can specify 0 0 and 1 1, something like that, okay. CBF 0 0 1 1, that, okay. Now if you want to define it, you can also input as a new function and just implement the values by hand. Depending on how many values you computed, it will take longer or not. I will show you how to copy paste this as function, okay. So we go back to SAP, we save this, and we also save the model. In order to have access to the interactive database, we go here to edit, interactive database editing, and one moment until I get this. So to load pattern definitions, response spectrum functions, and we have the table with user defined response spectrum, and we get this. Great. We can export to Excel or send the table to Excel, okay. And what's interesting is the following. You just need to take care of the structure of the format, and you can add here values. For example, for the moment resisting frame, I have here an Excel, okay. Here is the normalized spectrum, let's say for 0.3, 0.2, 0.7, 0.14, okay, 3 seconds, 2.5, and Q is 6.5, okay, done, okay. And I just need to take the values. I can have them, this is the design spectrum, I suggest taking the design spectrum, not implementing the elastic one and dividing by Q, because this part, it's true that you don't have many structures that rigid, and in that part it's not consistent with the design, okay. So you need to take the values of period and the values of acceleration, okay. Let's take this, copy, go to this, go to here, paste, okay, values and acceleration. Yes, match, okay. Now the only thing that I need to drag down, it's the name, okay, until the last value. If I want to add the next spectrum, I just go from the last value, as I told you, okay. Let's say for CBF, how much you had, Vlad? 2.5? You have inverted V, yes? And you have location, what location? Timișoara, București, Constanța? Timișoara, okay. So you can go with utility class high. We can take for inverted V, Q equal with 2.5, okay? Now we go with Q equal 2.5. You see that for 2.5 here it's a bit misleading. It's almost at the constant value, but it's correct, okay? It's just that we have a very small amplification factor or dividing factor. That's the reason for that shape, okay? And we need to take again this here, design here, yes, name, and that's all. Okay, now we go to SAP and we tell sub take from Excel, retrieve the table, okay? And it retrieves the table. Apply to model. Done. Okay. Define load cases, functions to check response spectrum. Centical base frame. It's correct, as it should be. Moment resisting frame function. It's correct, as it should be. Okay. I'm done in 5 minutes. Okay, you need to have the values. Okay, but you're done pretty quickly. You can do that by having, let's say, 5, 6, 7, 8 values to have the graph. It's correct, but if you want to be very precise, you can do that faster. Just that you need to have a spreadsheet with the computation for seismic load. Okay. Now we have this. Let's perform a modal analysis, but before that I want to check that we have all the sections assigned. So I want to add also for this beam okay. Select frame sections, default one, assign frame sections, on HEB 400, it doesn't matter, it should be more, but just to have all the sections assigned. Okay. Now, we mentioned regarding the orientation of the elements. We haven't checked them, okay? If you want, you can extrude the model, okay, to see here in displace option, general options. You can go with extrude, shrink objects fill, and we can see the elements. Now, regarding the X direction, which is this one, okay? I will put like that on your projector to see, okay, this direction. Are the flanges oriented properly for a moment resisting frame, or do we need to turn 90 degrees? Think again, what resists better bending, the flanges or the web? Bending. You have an IP section like that, okay? You have the beam like this, or you turn it and have it like that. The flanges are like that, okay? Then I have bending like that. It's correct or not? It's correct, okay? Now I need to check all the elements. You can also see your design theme. Here it's a bit tricky and it will be a discussion, because this column, this should be turned, okay? For first and foremost, this should be turned. This should be as they are, okay? These columns, okay, with the middle ones. Now let's check them. So we should turn in the braced these columns, okay, in the braced frames, because we have the flanges at 90 degrees and you are connecting braces on the web, which is not efficient, okay? We need to turn them. So this, and in the first frame, in the first base, sorry, in order to turn them, we need to go to specify a rotation of 90 degrees for the local axis. So we go to assign, frame, local axis, and we just put a 90 degree angle, okay? Check please check this part to see if it turns. Okay, so here. Okay, now we have the proper orientation also for that columns, and you see the local axis here. Okay, we can check the inner columns. They are oriented properly also for the moment resisting frame direction. Now, I suggest if you can, depending on your design theme, depending on your location, depending on the loads, you can have this column here. Just 1 second, because you have a bit of distance between what I'm showing on my screen and the projector. That column, you can have it pinned, or that being pinned with that column also in the other on the other end, and have just one bay moment resisting frame. Okay, such that you can design properly on 2 directions independently. If you cannot, because you cannot satisfy the interstory drift limitations, put it rigid. Okay, and we will check it using combined seismic action. Okay, but that interaction, it's not that easy to take into account in actual design. Okay, that's what I want to mention. Now, the rest, it's pretty much properly assigned. We can leave the initial visualization. Okay, and we can check, let's say, the modal response to see the periods and so on and so forth. We won't perform the design. I want to discuss about restraints, and then I will show you regarding imperfections and second order effects. Okay, now I will save, and the modal case, it's defined as default by sub, so you need not to define modal. You see here the modal case. Okay, okay, here you have modal. Now I will run it. I see the deformed shape from that, and I want from modal. Okay, I choose modal case, and the first mode, apply. Now this is our first iteration, and if I want to check how it performs like that, and I have a period of 2.97 seconds. Is it good, bad? Is it appropriate or not? What's the reasoning?
It's a bit too much.
It's a bit too much, but try to explain regarding the shape. Does it deform properly? Do you see a local deformation, like all the structure deforming, like torsion or translation in one direction, or is it something local? Yes, and basically you see here that the columns on the marginal frames are much more rigid on both directions. The columns inside are pinned on one direction, which is the braced one. They are just fixed on the other. So on that direction you have nothing to hold them like that. One key element here that we have not assigned, it's the diaphragm constraint. Okay, in Romanian, efect de șaibă rigid. Okay, now this helps us transmit the load to the slab, okay, to the floor. That's very important. If you do not have that, elements can vibrate independently. Now, in order to have it properly, we need to unlock the model. Every time you want to change something to the model, you need to unlock the model and assign it. Okay, I will select all the structure all structure except the lower restraints. Okay, I will go to assign joint constraints, and I need to specify the constraint. I will go with diaphragm constraint, add new constraint on z-axis because I want it on vertical, and you need to click here assign a different diaphragm. 1 second because it will delay here. Okay, you need to check this to have at each level a different diaphragm. Okay, and I need to select also that one when I click apply. Now it's a bit difficult to see, but I will show you. You see here a point in the joint and not at the end of the beam. And if I click on the joint here, it shows diaphragm 1, that's the name, _4, it's the elevation. So if I check at each level, I have the diaphragm effect. Okay, and if I go to assign joint constraints, I see all diaphragms that were defined at each level. This is what I want to see. Okay, now if you want, you can hide that, and these are the points that are connected at one floor which represent the diaphragm. Now I will run the model again. And from 2.95, how much I have? 1.12. Okay, if I click on animation, this is the first period. How is this performing? As expected or something unexpected? Okay, but let's discuss a bit regarding structural system. If you were to bet before running the analysis, what would have been the direction dominant? So, do you think this is the correct direction for the first deflection, for the fundamental mode, or on the other direction on the braced frame? Sorry? Think about the stiffness of different structural systems. Think about the system of a moment resisting frame compared to a braced frame. Which is rigid or more rigid than the other one? What's the reasoning of adding braces to a frame? Because we cannot satisfy the lateral displacement, so we need elements to make it stiffer such that the displacements are smaller. So the braced frame, it doesn't matter if it's X frame or V braced, we do not go into type of braces, but generally the braced frame is much more rigid compared to the moment resisting frame. And the eccentrically braced frame, it's in between. Okay. Now, given these facts, I'm asking again, the behavior is proper or not? Yes, it's proper as it should be. If not, then either something with the braces or something in that direction, it's misleading. So it's too small. You have the stiffness too low. Okay. Now we have 1.12 for a 4-story, 5-story structure as this one. You can evaluate pretty quickly using that formula from P100. T1 equals with 0.05, 0.075, doesn't matter, regarding on structural system multiplied with CT at the power 3.4, okay? Where CT it's in another factor function of other consideration. I think height, if I'm not mistaken, height. Now, about 1 second it's proper. If you have something over 2, it's completely wrong. Completely wrong, not necessarily with modeling. Maybe your sections that you selected for p-dimension, they are too small. Okay. Now you can have this as just some sort of initial check. Is it at first step? Is it okay or not? Now, if we go to check the second mode, the second period of variation, we have 0.75, and we see that we also have translation in this mode. Yes, on the brace frame, period lower, a bit stiffer, it performs properly. Okay, and let's check the third period. The third period is 0.59 and it's torsion. Okay, now you might be in the case of having torsion before translation. There are situations, there are different structural systems. I won't go into details. I have these types of structures for my thesis. If you have, for example, a central core. If you have a central core, basically if you have here, okay, a braced frame in this location, okay, in the center, it's like having a steering wheel. Okay, the lateral parts are much more flexible, and instead of performing as expected, you might have torsion. It's much more difficult to satisfy the displacement requirements for interstorey drift regarding that. So please check that you have, for this example, there should be translation and not torsion. There might be the case for third and second if they are very close, but we need to assess them and discuss them. Okay. Imagine that we did not even check for lateral displacement and so on and so forth. This is just model analysis. Okay. Now I will unlock the model and we will go to imperfections. Okay, I will show you how to for buckling analysis. I will show you how to define a buckling case. You need to go to define load cases, add new load case. Let's specify buckling for the name. Okay, and here for the load case type, instead of static we have buckling. Okay, now what is the combination for the buckling that we discussed? What's the most favorable one? Gravitational loading from persistent design combination, 1.35 dead and 1.5 live. Okay, I have 6 buckling modes here that I need to check. Okay, and I can specify more if I need more. Also in modal analysis we will discuss regarding how many modes you need to consider. Okay, but I want to show you how to assess this. Okay, this is the deform shape in modal analysis, and we can go to the deform shape in buckling. Yes, I have a buckling factor of 10.58, and if I check the animation I have something like that. Okay, what can you say about that? How can you describe it? Is it properly? It's not. What's the value? This is in the first mode. Okay, the columns were are very rigid. On the exterior? Okay. The output of buckling analysis regards how the structure vibrates. Eigenvalue analysis. Okay. Now it shows you basically function of the flexibility of the elements and flexibility or restraints. Okay. it shows you how the structure vibrates. Now, is this a global or a local buckling mode? First question. Again, animation, check again. It's not as pregnant as global as it should be, because if you check this, look, you have more displacement here at the base, but it's insignificant compared with the deformation of that columns. Okay, now let's understand why we have that deformation, because the columns are located in this location. Okay, sorry, they have pin supports on the perpendicular direction, so that is why they vibrate in that direction, because we do not have the web restrained. The web is flexible, and the web is the most flexible part of a double T section usually. Okay, so actually this behavior, it's quite suggestive on why it's like that. Okay, but it's not a global behavior, because mostly that columns vibrate on. We need to have an assessment of the global behavior. Now let's go in 3D and check for other mode. This is just the first. Let's go for the second. Mostly the same. Third, mostly the same. Fourth, fifth. Oh, something here it's interesting. I have 14.91, and if I go here, I see that I have a global buckling mode. It's clear that it's global, yes? It's clear. I have all the structure moving. It's not just one element vibrating due to the partial safety restraints. Okay? So actually, what's the value of alpha critic based on this? 14.91. Okay? Now, is this value larger than 10? Okay, which means that I have a sway or a non-sway structure. A non-sway structure. So I need not to consider an amplification factor in the combinations in the design, at least at this part, because maybe I can reduce a bit the sections and I will get 9. In that case, I need to amplify again. Okay. Whenever you are between, let's say, 8.5 and 11, you'll get in this type of loop. Okay. You either increase, you can reduce the bit the sections, or increase the sections, so on and so forth. So just make sure that before having the final sections, you also check this. Okay. Now, if you want to see all the buckling factors, you go to display, show tables, structure output, other input items, buckling factors, and here are the buckling factors. Okay, and actually the global one is this. So whenever you specify and you see in that template, okay, the factors initial design, final design, you need to have above 10. Okay, if you have not considered second order effects, and you say specify due to the fact that we have this value, the magnitude greater than 10, it confirms that our hypothesis in terms of first order elastic is valid. Why? Because in other case we need to amplify the effects of the lateral load having a first order equivalent analysis. So basically you say that the hypotheses are correct or not. It's very important to do that. Okay. Now, this regards to buckling factors. I will show you how to compute and assign imperfections. Now, this structure was an 18 by 18, yes? not this. We don't have a Bacchus today. Okay. Let's say you have values like 3, 4, 5. Because I have 50 minutes left, I will also pass a bit, and I want to show you other things. Now, you have the value for phi we discussed, okay? V, it's 1.35 multiplied with 4.5, it was the permanent load. I think 4.5, yes?
And the last level.
No, permanent on all levels. This is just very simple to have an... Okay, plus 1.5 multiplied with 3, 2.5? Yes. It depends on the function. 2? Okay, he has residential, okay. This is in kilonewton per square meter, okay. He has a surface of 18 by 18, okay. 18 by 18, this is square meters, okay. So, square meters I said, okay. So he has a force V of this multiplied with this to 1940 kilonewtons, okay. The force at level, it's phi. Let's define a angle, a very short one, in radians, and the forces should be, when you multiply, something like 15 kilonewtons, 20, so on and so forth. This is the total story force, okay. Let's take just one value. Now, for the corner column, FC, it's this multiplied with the tributary length. The tributary length for this one, it's 3 divided by 18. 3 divided by 18. And again, marginal and current, because you'll get messed up. F, it's marginal, and C, it's current. It's this, but double, okay? Now, if I check, I need to have that and that multiplied with 2, it's 20, okay? Because I have 4 currents. How I assign the loads? I can specify points like that, assign joint loads, forces. I will put on the current. Before that, I need to create a pattern. Define load patterns, let's say imperfections. As I mentioned, type order. As I mentioned, you should consider imperfection on X and Y. So imperfection X and Y, 2 types of loading patterns. Okay, please use at least one. That's mandatory. Okay, if you want the second, but you'll have 2 distinct combinations. I will use just one for the example. I will go to imperfection, and I need to put the force, which is now on the current columns. So it's FC, this one. The value is 6.67, but on what direction? This it's X, horizontal, Y it's vertical. On X, 6.67, okay? And you see the forces like that. You can put here 3.33, and you have on one level, okay? Basically, you go with the same magnitude on all, okay? Here, 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 here. Okay. Here, here, here. Here, 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 and here. 6.67, okay, And that's how you put imperfections.
In the y direction is the same, but
In other loading pattern. Yes. Imagine if you are to pick a direction, which is more favorable? The moment resisting frame, because it's more flexible. Okay. This is considering also the quality class for erection. Basically, if you have the technological requirements, okay, that's the global swing imperfection, okay, or butter technological, and it's much more flexible, the structure in that direction. That's why if you were to choose, pick that one. If you want to model both, great, exceptional. Now, apart from this, I want to show you how to take section cuts and relative displacements. So, I need two combinations to define. We will discuss also next time regarding dissipative combinations, because you have to define the case. I will show you the case here. You have two options. Either you define the case independently, seismic action on Y, seismic action on X. Either you take as combined action. So if you have S on X, which is moment resisting frame, it will be response spectrum. Okay. If you have just one, you go with spectrum from, it's an acceleration type load. On what direction? On, which is in global system, which is X. U1 or U2? U1, it's X in global. I specify moment resisting frame and I put the scale factor 1. Why? Because I already implemented the function as design. If you implement as elastic, you need to divide by Q. But I do not recommend that due to the reasoning of the first part, okay, the rigid one. Now, this is independently. If you have on Y, it's similar, but here instead of 1, it's 2, and you have CBF, okay? Now, you can take a case where you have something like that. Response spectrum, okay. You can have U1 with 1, U2 with 1. And it combines the effect of both, okay. And it does that using the directional combination. Okay, so you can check that column here with that, but also that's in non-dissipative. It's a bit more complicated. We will get also to that, but this is how you define that. Now let's have some combinations, at least for one direction. So define loading combination, add new combination. Usually I define them like ULS 1 to the number, and I put underscore G L win, so on and so forth, such that I don't have combination 1 or ULS 1 and I need to check in another Excel what does the name mean. Okay, so I do like this. I know the partial safety factor, so I have dead with 1.35 and live with 1.5. Okay, and I want to assign another combination which is dissipative. Sorry? Yes, it's the stupid delay. ULS2, let's say dissipative, so G and S from seismic, okay. GLS, okay. And I have dead with 1, live with 0.3, and seismic, let's state it on X, at least for this check, with 1. This is dissipative. Okay. If I want for displacements for serviceability limit state, so for drift, I have dead, live, and seismic with how much? 0.5 multiplied with Q, mu times Q. So for moment resisting frame, it's 0.5 multiplied with 6.5, which is 3.25. Yes. Okay. If you have a combined case for directional, you input there in that case for seismic action, you input 3.5 for one direction and for SY the corresponding value. Okay. And let's have another one for displacement at ULS or significant damage, which is dead with 1, live with 0.3, and seismic action is C multiplied with Q. Let's take C for the first iteration, 1, okay, and it will be Q, which is 6.5. Great. No. Okay, so I have the combination. I will run the model. I will show you how to check visually the displacements, and then using a very efficient approach. Now, let's see the deformed shape from displacement. It's like that, okay? Now, yes, I will show you next time how you can take combinative and so on and so forth, but let's assess for one direction. Let's visualize in Newton and millimeters. Do you remember what's the limit for the displacements? That's for serviceability limit states for a beam. 0.0075 multiplied with h, 4 meters, meaning 30. So we have a limit of 30 millimeters, yes? Now, we need to have the relative displacement. So if I go to this point, it's 11, minus 0, it's 11. First order, it's correct or not? Less than 30. Okay. Okay. Yes, the mouse is in other direction. Now, for the first story, I get 29 minus 11, 18. I get 44 minus 29. Okay, so on and so forth. You can do this much simpler, like that. Show for the joints the labels. Sorry? It will load. So I have the label of the joints 84, 86, so on and so forth. Go to define general displacements. Add a new general displacement. Now, here it will show you the relative displacement between 2 points, not having you to subtract each time. You get the actual value. Now, for joint 86, that's the ID. On U1, meaning on X, I put 1. If I want to assess also on U2, I put also on U2. And I add. For joint 85, I put minus 1, because you subtract from top to bottom and you get the relative displacement. Okay? So here you put minus 1. Add. So here it's for first level. I will create just one more. You have 87 with 1, 86 with minus 1. Okay. Now, when you run, you go to display, show tables, joint output, displacement, generalized displacements. I think absolute it's okay, and you check from serviceability, from displacement serviceability limit states for the interstorey drift. Okay, and you get this. How does it look? Fast or not? And you just compare that value, which is the absolute value, okay, it's 11, and 17 with 30. And you don't do that graphically and write and so on and so forth, okay? You just define once the general displacements. Don't forget to do that on X and on Y, and you will see on different combination what you want to assess, okay? Now, this is one thing, and from theta, here, from theta we get this. The only difference is that we don't take it from serviceability limit state, but from ultimate limit state, so it will be multiplied with another 0.5, okay? Another half, okay? Now, we need to discuss about the forces. The forces, you can take them from the diagram, and you will kill yourself if you have braces, because you will need to decompose on vertical axis and add them and so on and so forth. You can use section cuts, and I will show you how to perform 2 section cuts, okay? Now, the section cuts, imagine them as something like this. I will specify a rectangle that encompasses all the structure. The origin of the system, it's in the middle, and we have X and Y, yes, horizontal and vertical. We need to define a plane that encompasses our structure. To do that, we go to define section cuts, add new section, and here you will specify quadrilateral cutting planes. Before that, I want to change the system. Okay, define section cut. Good. Now, you need to specify the 4 points. You can start from wherever you want. I suggest starting from somewhere here, okay? That point will have what coordinates on X and on Y, considering a 1 meter extension from the facade. Sorry? So you have half of the structure, meaning 9 meters until here, and 9 meters until here, okay? This is actually minus 9 plus 9, and if I want another meter, it's minus 10 and 10, so it's minus 10 and 10. And on Z, if it's on first floor, usually at first floor you will have problems at 1 millimeter, you can cut at 1 centimeter, so it's 0.01. At next floors you can cut at 1 millimeter, so 4.001, okay? For the next point, which is, where's my mouse? Somewhere on the right corner, it will be on X 10 meters, on Y 10 meters, on Z 0.01. Lower we have on X 10 meters, on Y minus 10, on Z 0.01. and the last one, it will be minus 10, 0.01. And you can check it's okay, yes? As output, you want to specify F1, F2, F3, meaning forces on X, Y, and Z. So you'll need F1 and F3, or F2 and F3, depending on your direction. And you do that. I will just show you for this one, you need to specify for each level another section cut, okay? You run the analysis. Show tables. At structure output, other output items, section cuts, you need to specify the dissipative combination. And the dissipative is, in our case, this one, okay? This. And I have F1 and F2. You take the values in absolute value. So I have F1 on X, which is shear force, V total, and F3, which is P total. And imagine that you have another section cut 2, 3, and 4, and 5. You take that you go in an Excel and you define something like this for all 5, okay? You take this as absolute value and this an absolute value. You have the relative displacement from displacement for ultimate limit state combination. You put the ratio and you get theta on X and on Y. On Y you need, instead of F1, you need F2. Here we do not have F2. Why? Because we have seismic action just on one direction. Okay? And you'll do that pretty quickly and not hate yourself computing theta, okay?